Okay, our first problem involved a current running through a coil along the x-axis, 300 loops running between x equals 0 and 10 centimeters, cross-sectional area of the loop 3 square centimeters. Looking at the loop from the side, assuming that the current is running in this direction, we have current coming out of each loop here with the axis, and current running coming out of the board with each loop at this point and running into the board at each of these points. So we conclude that we create an imaginary loop running from way up here down to here, across and way back up, running across the x-axis. As we established previously, the contribution of the enclosed charge, the enclosed current being these currents running into the board, the contribution of the, back up. We're doing a line integral around this imaginary boundary, and that boundary encloses all these currents. The part of the line integral that corresponds to this side is equal and opposite to the part of the line integral that corresponds to this side. The line integral of the part that's way far away is essentially 0. So the only part of the line integral that applies, that has a non-zero result, is the integral from 0 centimeters to 10 centimeters along the x-axis. So knowing by Ampere's law that the integral of B dot ds has to be equal to the enclosed, to 4 pi k prime times the enclosed current, we obtain all of this, and magnetic field being constant, we conclude that B times 10 centimeters is 4 pi k prime times the 12 amp current times the 300 loops. The 300 loops being relevant because we have 300 of the 12 amp currents penetrating the loop, rather penetrating the plane defined by the loop, that portion of the plane bounded by the loop. The result is obtained in a fairly straightforward way, and you'll notice that I had to reason out the units of K prime because it's easy to confuse those units. Just to be sure I had it right, and I really didn't have it. I wasn't sure whether it's Tesla meter squared or whatever. But the contribution of the magnetic field is K prime I delta L divided by R squared. We have a cross product with the unit vector R divided by its magnitude, but it carries no units. The units have to come out Tesla, and units of I are amps, units of dl over R squared are reciprocal meters. It follows that the units of K prime have to be Tesla, so that we get the Tesla, meters, so that we cancel the reciprocal meters, per amp, so that we cancel the amp, so that the magnetic field is this times the 3600 amps that we get when we multiply the 12 amp current by 300 divided by the 10 centimeters. And when that calculation is done, I believe we get 400,000 times 10 to the negative 7th Tesla, 4 times 10 to the negative 2nd Tesla. We then use this calculated field to calculate the flux of a single loop. The flux of a single loop is just the perpendicular component of the magnetic field times the area. The magnetic field, by right-hand rule and so forth, is in the x direction perpendicular to the plane of each of these loops. The area of a single loop is 3 times 10 to the negative 4 square meters. When we multiply the field by the area, we get 1.2 times 10 to the negative 5th Tesla meter squared. Total flux is 300 times that because we have 300 loops, and we get, I believe, 3.6 times 10 to the negative 3rd Tesla meters for the total flux.